Okay guys, so we designed the feedback control, state feedback control law by the first method I taught you in the previous class, if you remember. Now, as I told you, we have two more methods to determine the gain matrix of U minus Kx, that's right? So in the state feedback control law, our function is to determine the K. And I did the simulation by MATLAB, by OD solver of the MATLAB in the part 12, that's right, or part 11. So, and now we are continuing. So remember that we had this LTI system, x dot is ax plus bu, and the a was what? A was 0, 2, 0, 0, 0, 1, minus 1, minus 3, and minus 4, right? And the b vector was 0, 0, and 1. Now, state feedback control law, we wanted to have what? We wanted to have, if you remember from the previous class, these dominance poles or the eigenvalues of the system. S1 is this, S2 was this, a pair of complex conjugate poles or eigenvalues, and S3 was minus 5. That's right. And we want to go to what? To origin. That's right, as is seen in the MATLAB coding. So, and we discussed why we selected these, and obviously, if you remember from the previous class, and if you see that the MATLAB code I upload on the Blackboard, so we have three state variables, x1, x2, x3, because it's a third order system, 3 by 3. So I was starting from some non-zero initial conditions. For example, we had this, that's right, remember, without controller we had these, that's right, say these, we had these, so all of them without the controller, if I'm not wrong, was settling down from undergraduate control in 15 seconds. But after applying the state feedback control law, as I did in the previous class, you can see in the YouTube, they were doing this. Remember, they were doing this, all of them. That's right. They were settling at, say, if I'm not wrong, around 4 or 5. That's right. Settling time was 4 or 5 seconds. Please double check the previous video. So why this happens after applying the feedback control law? Because remember, on the graduate control and the vibration, that when you have a pair of complex conjugate poles, so S or S1 and S2 or P1 or P2 or lambda 1 or lambda 2 poles are the values, you're going to have this general format, zeta omega n plus minus j omega d. That's right. This is undergraduate control. That's right. And the vibration. So the zeta was damping ratio, if you remember. Damping ratio. Yeah. So omega n was the natural frequency of the system. Natural frequency of the system. And omega d was what? Damped. This D stands for that. Damped natural frequency. Damped natural frequency. Right? So now comparing this with this pair of complex conjugate poles, compare this with this, right? And this is number 1 here, that's right, and 1 with this. You can easily understand that zeta omega n is 1, and the omega d is also is 1, for God's sake, that's right. So, but we know that omega d from the undergraduate vibration, undergraduate control, is omega n when you have an underdamped system. This, okay, is 1 minus zeta square is 1 here. So if I divide relation number 1 by 2, if I divide 1 by 2, this you have this omega n 1 minus zeta square divided by zeta omega n is how much? 1. This omega n with the omega n goes to Denver, so what you're gonna get is this 1 minus. I'm doing this because you wanna know why your boss asks you design a feedback control law to have such a pair of complex conjugate poles, and how we get these plots. This is not by accident, okay? Is equal to by zeta. So squaring both sides, you get 1 minus zeta square is zeta square. So what you get is 2 zeta square is 1. So zeta is root of 0.5, right? And the answer is gonna be 0.7. Let me double check. I'm not God. Okay. So the answer is gonna be okay. I got it. 0.5. Yeah, almost gonna be ballpark gonna be 0.7. And this is valid because your boss telling you design a controller, this U that gives you a underdamped system, the dominant underdamped system. So zeta is smaller than 1, so your system is right. So by having that, you can get from here, from relation number 2, you can get omega n is 1 over zeta, which is 1 over zeta, 1 over 0.7. So natural frequency of the system, okay, after designing the controller is 1 divided by this. It is ballpark is 1.4, right? Radian per second. And I taught you on the undergraduate control and also vibration, zeta is dimensionless, that's right. So let me write it down here. I'm going to do that. So here we go. So zeta was 0.7 and the omega n was 1.4. Hold on, this has got glitch here. So what we're going to do with these numbers, okay? You are a control engineer, guys. You have to open your eyes. Okay? You have to interpret the numbers. You have to know the physics of the system. So in undergraduate control, if you don't know, as I showed here and you saw in the MATLAB in the previous class, the settling time was 4 or 5 seconds. This is for, let me change the color. This was for without controller, the red lines, without controller, that's right. And the blue lines, if you look at the MATLAB code I did in the last class, this was with the with controller, with a state feedback controller, with controller, these blue lines. So you see that I decreased the settling time from 15 seconds to 4 or 5 seconds. I wanna get this by this dominant complex conjugate poles, this 4 or 5 seconds. In undergraduate control, I taught you the settling time is 4 over zeta omega n. If you forgot in the vibration, please go and read it. Or is 3 zeta omega n. So this is based on 5% criteria. This is 2% criteria. That's right. It means that your final response becomes only 5% after your steady state values and 2%. So I'm going to get this. So 4 divided by zeta. Zeta we calculate is 0.7 multiplied by 1.4. If you do that, you're going to get, let me do that. You're going to get almost 4 seconds. Oh, what happened? 4 seconds. Bingo. You see? So your boss intentionally told you guys, I want to have this dominant complex conjugate poles or eigenvalues of the system. that you design a controller for me. Why? Because I want to have, by this number, 4 seconds of settling time. And we did it together, that's right. And in the previous class, we had, we calculated gain metrics as how much? 493. So in the MATLAB, we implemented this, and the control input was minus kx. Remember that in the coding? Means we did exactly in this MATLAB. 493, and we have 3 state variables, x1, x2, x3. So obviously this is 1 by 3, this is 3 by 1, so we're going to have a scalar u, because this is CISO system, single input, single output system. Okay? So everything is based on the logic. There is no gambling, no chance. Okay, you have to understand what you are doing. Okay, so the second method that you can calculate the gain metrics, that is, this course is for that, is the determination of metrics gain metrics, okay, using direct, this is the second method, first we did direct substitution method. Okay, so this is very useful, because if the order of the system is smaller or equal to 3, means you have third order system, second order system, means that third order system means that you have 3 state variables, that's right. Second order system, third order system, you have 2 state variables. For the lower order dynamical system, I recommend that you do this after graduation. In the final exam, I'm going to give you a challenging problem. Okay, so now how is that, guys? Look at here. So this is the general LTI system. X dot is equal to AX plus BU, and as we designed KX, this is that we are doing this, right? State feedback. So what we get here is this, as I did, A minus BK in X. Remember? Huh? So if I apply, guys, I have done this several times. I'm doing Laplace inverse, Laplace transform. So you're gonna have x of s, remember, minus x at time 0 initial condition is A minus BK in x of s. That's right. So if I move this to this side and this to the other side, what I get is this. X of s, this is common factor, comes out s I, because we are dealing with the matrix, not the number, not 1, minus A minus BK, okay, is equal to x naught. Remember? So if you want to find the x of s, that's right. Let me write down here. So x of s, let me write it here and again, is Si minus A minus BK is equal to x at time 0, state vector. So x of s, for God's sake, gonna be, it's very easy from high school algebra, Si A minus BK inverse in x at time 0. But again, as I'm refreshing your mind from the middle school, a matrix inverse is matrix adjugate over determinant of the matrix. Oh, you see that the puppy is screaming. It's very cute. Okay, so the same here. So x of s, again, here for this system gonna be Huh? Please don't do that. I'm teaching. A minus bk adjugate divided by determinant of Si minus A minus bk in X. This is S domain, okay? So you see this determinant of this. So this gives you what? The poles of the system. Remember, I was doing that. This is the poles of the system. Poles or eigen values. That's right. So you see that this is very easy. So this in the denominator gives you poles eigenvalues of the system. So what I'm going to do, I'm going to say, okay, after I designed my state feedback, this minus kx system, it's going to give me the poles eigenvalues of the system. So I'm going to say Si minus A minus bk is equal to what? This gives me poles eigenvalues. This gives me the poles and eigenvalues that I want to design. Okay, your boss gives you. Okay, I'm going to say S minus mu1 for this system, S minus mu2, and S minus mu3. Because why? I have third order system, so I have 3 desirable eigenvalues of the system. That's why we name it pole placement. Clear? So, but for an nth order system that you have n state, you have n desirable poles eigenvalues, you're gonna be mu n. Okay, but today, because the example is third order system, so I'm gonna put a circle on this. We're gonna solve this. This is very easy, guys. Easier than the previous cases, right? So let us do that. So for this example, let me see if it's recording. Yeah, for this example, you get Si minus A minus bk. Let us do that. Determinant of Si. Si is this. S in identity matrix. Bingo. Minus A minus bk. A, we have it. This is A matrix for this, and the B. A minus bk. So this is your A. 0, 2, 0, 0, 0, 1. Let me double check. 0, 0, 1, minus 1, minus 3, minus 4, minus 1, minus 3, minus 4, minus bk, plus b. Your b is this 0, 0, 1. This is not magic, guys. This is the given information of the problem. In k, k is k1, k2, k3. Determinant. Right? So the trick is here, guys. This is 3 by 1 matrix. This is 1 by 3. So the result of this is gonna be 3 by 3 matrix. That's right. So let us do that, because you have to sum and minus and subtract a lot. So here gonna be 0, 0, and 0, 0, 0, 0, k1, k2, k3. You have to be very careful about this. Okay? If you respect what you learned in the middle school and high school, you are fine. So this is equal to, after subtracting this from this and plusing and adding to this, so what you're gonna have this, for God's sake, you're gonna have S minus 2, 0, 0, S minus 1, so plus 1 plus k1, so k1 plus 1, 3 plus k2, so it's going to be k2 plus 3, and 4 minus 4 plus k3 plus 4. We got it. This is the determinant, this side. This side. So now let me go to the next page and calculate its determinant. Here we go. This is determinant of, let me change the color because it's too much red. Determinant of s minus 2, 0, s 0, s minus 1, k1 plus 1, k2 plus 3, and k3 plus, oh, we have also, I see that I'm missing, you have s also here, is plus s, see, s plus 4 plus k3, see, s plus 4, that's right. So determinant of this is s in determinant of this, s minus 1, k2 plus 3, k3 plus s plus 4, plus 2 in determinant of this part, 0 s k1 plus 1, k2 plus 3. Here we go. So this is equal to s multiplied by s multiplied by k3 plus s plus 4, this by this minus this by this, plus k2 plus 3 plus 2 minus s k1 plus 1. Here we go. Okay, so stop it. I see that guys, I made a mistake here, guys, sorry. So this is I was wondering where's my mistake. So this is 2 in these elements, 0, yeah, minus 1, k1, and this is I see that s in this, yeah, it is k3 plus s plus 4. No, I got it. Okay. So, and now the result of here is gonna be k1 plus 1. So if you multiply all of them, you're gonna have this s cube plus s square k2 k3 plus 4 plus s in k2 plus 3 plus 2 in k1 plus 1. So this is the result of that determinant. But this is equal to your desirable poles. Your desirable poles is this. Oops. Desirable poles are this. 1 minus 1 plus.
I can learn to understand you much better if I can get familiar with the way you talk.
What? I don't want to talk. In s minus 1 minus g, in s minus 5. That's right. So if you simplify this that we did in the previous class, remember it was s cubed plus 7s squared plus 12s plus 10. So now what you're gonna do, just compare this in this and that. S cubed coefficient is 1, here is 1. Here is k3 plus 4, here is 7. So you can say k3 plus 4 is 7, so K3 is 3. Bingo. This is S is this is 12. So K2 plus 3 is 12. So K2 is 9. Bingo. And this is 10. This is called constant. So 10 is equal to 2K1 plus 2. So K1 is how much? Gonna be 3. Sorry? Huh? Let me double check the previous class. Yeah, so yeah, this is 4. So as we know, as we derived the previous class by the method number 1, again your gain matrix becomes 4, 9, 3. Bingo. Now again you can go to MATLAB, develop the code that I did, and do more things. Okay. So I wanna go to the next page, and now let me, you know that on Thursday I'm sending you. Okay. This is recording. Come on. Yeah. So now the third method that you have to know, and after graduation you can use MATLAB and avoid these kind of calculations, is the determination of K gain matrix based on Ackermann's formula. Ackermann. Okay. These are interesting, guys. So Ackermann formula is this, guys. This is how we calculate that. It is K is equal to 0, 0, 0, 1 in inverse of controllability matrix an minus 1. This is controllability matrix, right? In phi of A. What is phi of A? Phi of A from the KLA Hamilton I taught you in the class. I'm pretty sure that an eigenvalue, a vector is a matrix satisfies its own eigenvalue problems, right? An plus alpha 1 an minus 1 plus an minus 1 a plus so alpha, these are alpha, not a, alpha and alpha n in I. So I remember Clay Hamilton I taught you, where alpha i's are coming from, again, this your desirable poles or eigenvalues of the system provided your boss that he's paying you. Sn alpha 1 Sn minus 1 plus alpha n. So just replace them here. Simply that this goes here and this goes here and the middle goes here. So this is Ackermann. Okay, Ackermann formula. So now what you're gonna do, the same problem. So controllability matrix, remember, for the controllability matrix that we derived in the previous class was, go and look at it, for this problem was 0, 0, I mean this controlability matrix. This is M 0, 0, 2, 0, 1, minus 4, 1, minus 4, 13. But Ackermann says you have to calculate its inverse. That's right. So having that, I'm gonna calculate this part first. Look at here, guys. I'm gonna calculate this part first for this problem. So it's gonna be this third order system, 0, 0, 1, third order system, in 0, 0, 2, 0, 1, minus 4, 1, minus 4, 13 inverse. If you do that, let me do it with MATLAB because you're gonna say how. Okay, so okay. All is coming up hopefully. Yeah. So the result is come on. See, it is what is it? Oh, I forgot to bring yeah. So it is 0 space 0 space 1. Oops. 1. And now multiply by let me write like this, inverse of that controllability matrix, 0 space 0 space 2, and now the next line is 0, 1, minus 4, 0 space 1 space and minus 4, and the next line is 1 space minus 4 space 13. Here we go. And now I have to close it. Let me double check with you guys. 0, 0, 2, 0, 1, minus 4, controllability matrix, 1, minus 4, 13, 0, 0, 1. So this part, if I do that, answer gonna be 0.500. That's right. So this part's gonna be, come on, okay, it's recording, yeah, okay, so it's gonna be 0.5, 0 and 0. Now I have to find, after finding this, I have to multiply by phi of a. Phi of a, as we did in the part 2, can be found as 0 like this. Look at here, guys. Yeah, we did that. This is the same term, that's right, in the part 2. Same term. So now let me go to the next page. Come on. Okay, so now having s minus mu1 in s minus mu2 as we did in part 2 today, s minus mu3 we derived as s cubed plus 7s squared plus 12s plus 10, and knowing that this is alpha 1 7, this is alpha 2 and this is alpha 3. Here we go. That's right. So now you have to calculate phi of A, Ackermann. Phi of A is matrix A power of 3 plus alpha 1. Let me write this. Look at here, guys. Matrix A power of 3. Matrix A was 0, 2, 0, 0, 0, 1, minus 1, minus 3, minus 4 to the power of 3. You know that this is matrix we cannot do by element by element. You have to calculate this A in A in A. You have to do like this, okay? Plus alpha 1. Alpha 1 is how much? 7. In A square. Again, 0, 2, 0, 0, 0, 1, minus 1, minus 3, minus 4 square. Again, you have to calculate A multiplied by A. Plus alpha 2. Alpha 2 is 12. So you're going to have 0, 2, 0, 0, 0, 1, minus 1, minus 3, and minus 4. Power of 1 plus I plus 10I. See here? 10 alpha 3I in identity matrix. Here we go. Okay. So if you calculate that, I have in the piece of the paper. So the phi becomes like this. Please do it at home as homework for yourself. 8, 6, minus 3, minus 1, minus 3, 3, 3, 11. So we got the phi. Okay, now the gain matrix, as we said, Ackermann says, this is this part multiplied by phi. Here we go. It's gonna be 0.100 multiplied by phi, which is 8, 18, 6, oops, minus 3, minus 1, minus 3, 3, 3, 11. And for showing that this is right, I'm gonna show it here. See here. So I need keep it. Oh, it must goes down. Okay. Keep it. Okay. So if I go to the upper line, no, I have no keypad today, so Control C and Control V. So it is 0.5, 0.5, and this is 0. This is no inverse, and the phi is how much? 8, 18, and 6. Next one is minus 3, and space minus 1, and again space minus 3, and the last line, to avoid this torture, is 3 space 3 space 11. So let me double check. 8, 18, 6, minus 3, minus 1, minus 3, 3, 3, 11, and this is the first part. So what we get? What invalid expression count? Oh, I have extra things here. Sorry, guys. Control C, Control V. This is extra here. You got 493 as we calculated in method 1 and method 2. So the gain matrix again, becomes, in 3 method, which is very famous for state feedback control law, is 4, 9, and 3. The next class I'm going to go the MATLAB version of this, okay? After graduation, you have to know how to do the MATLAB rapidly after graduation. Okay, next class is going to be MATLAB version of this, MATLAB. Okay, here we go, after graduation. So now let me give you, that's it. So next class I'm going to talk about the MATLAB version and we continue the class.